There it goes now. Okay. Okay, guys, so the graphical method, if you go to your notes, this is on chapter 9, I think. Last chapter in your book, but one of the most important chapter for your for your assignment. Okay, so this is framework chapter 9 here, and it says here page 56 in your notes, the English notes, page 56. Okay, guys, and for your purposes, the first few pages is just, they talk about determinacy. Before we start analyzing any frame, and if I'm talking about the frame, I'm talking about the truss here. Who don't know what the truss is? Okay, if you don't know what it is, I'm quickly going to show you a video. I'll also upload these videos. Let's choose videos. Okay. Now, does this look familiar? This is a roof truss or a roof frame, and we're going to analyze this. And why do we analyze a truss? Because it's a bit different than last time I've seen you guys. We've done a static analysis of a beam. That's the most simplest form of analysis we can get. Now we're going to look at analysis of frames or of trusses. But we need to know what the internal forces is in the truss. We need to know, is this member here, if I'm talking about the member, I'm talking about from this node here, this is called the node, to this node, and from this node to this node. I need to know what the internal forces is. Is there tension or is there compression in these members? And we're going to calculate this using two methods. First method is the graphical method, and the second method is the method of sections. That's the mathematical method. Okay, there's also a third method, the method of nodes. Some of you might have learned it at school already. You can do it to do your own checks. I'm not going to go into that. Okay, so on this video, which I'll upload, they put compression from the top. Now that's typically what we get from loading. For instance, if there's snow on your roof or wind loading. So that piston from the top keeps on compressing. Is this video playing? Yeah. Okay, so it keeps on applying force from the top. What would your guess be? Where will it break?
Closer to the ends.
Closer to these ends, to the bottom or the top?
Bottom.
That would be my guess as well. Would it be in compression or in tension at the bottom?
Tension.
Tension. Okay. Normally it's in tension, guys, but we always check it with the graphical method, because if a frame gets complex, you'll see at one stage it... is this video slow? Okay. You'll see that you can never really determine if it's in compression or tension just by looking at it. You get the idea, but it's definitely not. It's not that simple. Okay, just going to fast forward. We can sit here forever. You can see it pressing down when I jump. You can see it pushing down. Okay, it looks like it broke down here. I can see there's a split or something. Okay, it looks like it broke down there. It looks like a tension from that bolt. Okay, but there's many of these videos on the internet. You can check it out. This is just a frame test. We also test this in the lab with the scaled models. This one is nice and fast. So we add loading to your truss. These guys is, it's not supposed to happen like that, but okay. On this frame you can clearly see the tension will be where? on this member here.
Oh.
Okay, it already snapped. Okay, so it's a scaled member. If I go back here in the beginning, just to show you the figure. Okay, here's your figure. When I add loading here, I pull it down over here. So this member is going to be in compression or tension?
Compression.
Compression. And this member will be in
Tension.
You can already see it deforming here. Okay, this member will be in compression or tension? It starts getting more difficult to see it. And the more complex it gets, space frames and so on, where you see in roofs and so on, gets too complex. You can't just determine it by looking at it. So this is what we're going to do. We're going to calculate this graphically. Okay, just the last video here, showing you a truss of a breach. This is a nice video. There you can see a space frame or a warren truss. I'm just going to skip this, guys. You can look at it at your own time. This is all the breech supports, different types of supports we get at the bottom. It's just a span, I give it. That's the connections. Okay, so on a frame like this, how do you determine if this member is going to be in tension or compression? It gets too complicated. Can you see that, guys? And this truss is running in this direction as well. So I'm going to play this. Luckily nowadays we get software. There you can see the lateral supports, lateral trusses here as well. So it's supported by trusses here. It works similar to a beam, but it's a made-up structure of different members. Okay, that's all you need to know. And what I'm going to tell you today, guys, is a recipe how to do this. I just want to get my example open here. Okay, now guys, I've already sent some of these examples to be uploaded on MyCloud. You can get us from MyCloud or from Blackboard. If it's not up there, guys, please email me so we can make sure that it's available for everyone. Okay, now I'm going to draw a truss up here, and then we're going to start with the analysis. In your notes, there's some examples. You can read through this, but if you just do what I do here, step by step, you should be fine. Okay, so I'm going to draw a truss up here. I'll also upload this example if you don't want to make too much notes. Okay, so we've got 1, 2, 3, 4, 5 triangles in here. Then I've got a support here, a column. And I also got a column here. I'm going to call this column A, support A, support B. What else we got on here is we got uniform distributed loads over here. The first one is over here. And this is 5 kilonewtons per meter, and we've got a second load up here which is 20 kilonewtons per meter, and we've got no point loads. So yours on your assignment looks very similar to this, except the one in your assignment you've got external loads. We've got loads over here as well. Okay, so it's pretty similar, the one I'm doing now. So if you follow this and you know the rules, you should be able to do your assignment. Okay, now what is the first thing we need to do when we analyze any structure? We first need to calculate what? Similar to beams last time, we need to calculate the reaction. So I'm going to write this recipe down here. First one, reactions. Okay, let's calculate the reactions firstly. Okay, so how do I determine my reactions? Same as for the beam. I'm going to pin it at A. I'm going to take moments about this point. And then I'm going to do this again. I'm going to pin it at B, and then going to take moments about this point. So, my formula for this is sum of the moments about point A equals 0, and we take clockwise moments as positive. Okay, so if I pin this at A, what forces do I got in here? I've got the 5 kilonewton load here. I've also got the 20 kilonewton load here. And I've got one reaction over here. Okay, that's what I've got. So, let's quickly do the calculation here. If I pin it at A, the first force I get right off my reaction here is 5 kilonewtons for 5 meters. Okay, we need some distances in here. Okay. Here is also 1 meter. Okay. Now, if this height is 1 meter and the distance to here is 1 meter, what is this angle here?
45 degrees.
45 degrees. Okay. So, in the exam, I'm going to hand out a graph paper looking like this. You're going to get one of these graph papers. And also your assignment, you can print off a graph paper or you can buy a graph paper. You can also do it on AutoCAD if you like. Okay, so what you do, guys, is on the graph paper, I can only ask you 45 degree angles, am I right? I can't ask you to draw 30 degree angles, it's going to get complicated, am I right? So I'm going to stick to 45 degrees in the exam and for your assignment. Okay, so normally you're going to see 45 degree angles. Okay, so your Cremona diagram or your Maxwell diagram must be drawn on graph paper. Okay. So let's start on the first one, reactions. So if I take moments about point A, the first force I'm getting is 5 kilonewtons for what distance? 2 meters. So it's 5 times 2, so I can use my bracket here. 5 meters times, 5 kilonewtons, sorry. Times 2 meters times what perpendicular distance? So this force is going to be transferred here in the middle. So I'm converting this into a point load. So what distance is it going to be to this point, the perpendicular distance? 1 meter times 1. Is it going to go clockwise or anti-clockwise around my point?
Clockwise.
Clockwise, so it's going to be positive. The next force I'm getting here is reaction at B. So let's write this down. The reaction at B is going to push anti-clockwise around this point, so it's going to be negative. Reaction at B times how many meters? What's the perpendicular distance to here? 1, 2, 3, 4 meters. Okay, and then the last force I'm getting on here is this 20 kilonewtons per meter. I'm converting this into a temporary point load. Is that going to go clockwise or anti-clockwise about point A? Clockwise. So it's positive 20 kilonewtons per meter times how many meters? It's over a distance of 2 meters times what? Perpendicular distance. So the perpendicular distance from here to here will be what? 5. 2, 4, 5 meters. Okay, and all of this must equal to 0. That's what my formula here says. Sum of my moments about point A equals 0. Okay, if you've done this, guys, we can quickly calculate the reaction at A. Reaction at B. All you do, you transposition this to the other side, and you calculate B. Will you be able to do that? We've done it last time, am I right? Will you be able to calculate B? Okay, so it's going to be 4B equals whatever else. You transfer all of that to the other side, and your answer there, you divide by 4, you get your RB. So your RB in this case, you can check this answer, but it should be 52.5. kilonewtons. Okay, so you can write this in if you want to. I like to write it on my graph, so it's 52.5 kilonewtons going upwards. Now, just by looking at this graph, guys, what's going to happen here? If I have a 20 kilonewton load for 2 meters, that's 40 kilonewton load, and I pull it down over here, what will happen on this side of my frame? It's going to want to lift up. It's like a seesaw. So that's why I haven't put an arrow on this one directly, because there's probably going to be uplifting. So to keep this in equilibrium, what must happen here? I need to hold it back. So that's what's going to happen. We don't know it now. The way we do it, if we take moments about point B and this answer is negative, then we know the arrow is going downwards. Okay, so let's do that. So we take, again, clockwise moments is positive. Sum of the moments about point B this time equals 0. Okay, so I'm going to put it here. So let's start on all the forces on the right side of this. So that's again going to be 20 kilonewtons for how many distance? 2 meters. 20 times 2 meters. And the perpendicular distance to this point here is going to be 1 meter. And this is going to be positive or negative? Positive, because it's going to turn clockwise around this point. The next force I'm getting is 5 kilonewtons per meter for 2 meters again. Times 1 perpendicular distance. From here it's going to be 1, 2, 3 meters. Clockwise or anti-clockwise about point B. It's going to push this way around point B, so it's going to be anti-clockwise, it's negative.
Why is it times 3?
Perpendicular distance. So 5 times 2, 5 kilonewtons per meter for 2 meters. That gives me 10 kilonewtons. And this, you convert this into a point load in the middle here. So it's going to be 1, 2, 3 meters to point B. Okay. And then my last bracket here is for the reaction at A. So let's calculate the reaction at A. So this one is going to go anti-clockwise, so it's going to be negative. Okay, I'll take it as positive, negative now because my arrow is showing downwards. If you take it as arrow going upwards, your answer will be negative. Okay, so going anti-clockwise, so it's negative, and that's going to be the reaction at A times how many, what's my perpendicular distance to B now? 1, 2, 3, 4 meters. So this one is perpendicular 4 meters. So all of that equals to 0, because that's what my formula tells me. Okay, if I calculate this, this should add up to reaction at A equals to 2.5 kilonewtons. Okay, if I had this as a positive, what would happen here?
Negative.
Negative. Okay. So the example I got here has got a negative, so you know your arrow must go downwards. Okay, so I'm going to remove all these temporary points I've used, the conversions, and I'm just going to write in here 2.5 kilonewtons going downwards. How do you check yourself that the whole structure is in equilibrium?
Sum of all forces.
Sum of all forces going downwards, let's check that. That's going to be 20 times 2 meters. Plus what? 5 times 2 meters. Okay, and this must equal to the forces going upwards, or the reactions. Let's rather say the reactions. And this one is 52.5 kilonewton going upwards, and minus 2.5 going downwards. Kilonewtons. Okay, so this equals to, on the right hand side, 52.5 minus 2.5 equals to 50 kilonewtons. And 5 times 2 is 10, and 2 times 20 is 40, so this also gives me 40 plus 10 is 50 kilonewtons. Okay, so this is the test. Yeah, do you want to ask a question?
Can't you, after you've worked out the first reaction, just go to that sum and figure out the missing?
You can. You can. You can do it as well. After you calculate the first reaction, or this reaction, you can obviously, just by doing this balance, you can automatically calculate what the other one will be. But in the exam, you won't get a simple one like this. You get loads of point loads, and you got loads of UDLs. If you make a mistake in your first calculation here, then you can't check yourself. Okay, so rather take the moments about point A, take the moments about point B, and get your answers and check them. Okay, it's just a safer option. Okay, now that covers my first part of my recipe. Can I take this section off here? Okay. Okay, so the second part of my recipe is Bose notation. Bose notation. Okay, the way Bose notation works is we need to number all these frames. We need to get numbers for them. So I'm going to call this member A1, B1, and so on. But the way we number them is to keep everyone's notes the same. We always start left of my left-hand side reaction, and then we go clockwise around. So we first name all these members on the outside, and then we number them in the inside. And the way we do it, we go from force to force. Now, if I convert this UDL into a temporary point load here, and I member them from force to force. So the first force is this one, then I go all the way around, and my next force here is in the middle of a member. Will this work? Because this member will have two numbers. So instead of converting it into a force going down the middle, what we do is we take half of the weight here, which is 20, force down, is 20 kilonewtons per meter for 2 meters. So that gives me 40 kilonewtons. So everyone okay with that? And I convert that, half of that is going to the one side of the node on this side, and half of this is going down here. So how much is going down on the right hand side here? 20. So it's 40 divided by 2 is 20 kilonewtons. And on this side again, 20 kilonewtons. So what happens on this point here? It's 52.5 going upwards, and I've got 20 going downwards. That gives me what? A resultant of 32.5 going upwards. Yeah, you're right. Okay, same over here. 5 times 2, which is over 2 meters, gives me 10 kilonewtons. Half of that is going to this node. That gives me what? 5 kilonewtons. And 5 kilonewtons going down this side. So that's also 5 kilonewtons. So what's the resultant over here?
7.5.
Yeah, 5 going down plus 2.5 going down gives me 7.5 kilonewtons going downwards. Okay, so that's the first thing we do. Now to start with my Bose notation, the first force I'm getting is here on the left hand side. And the first, I'm going to mark this in blue pen. First other force I'm getting is all the way down here, over here. And everyone sees I'm starting left of my reaction, and I'm going all the way around to my next force, this red line here. And I'm going to call this member A. From this force to the next force, which is here, I'm going to call member B. From this force to this force will be C. And from this point to this point is going to be member D. Okay, so Bose notation on the outside, we draw this lines from force to force. So what would happen if you had a point load down here? You would have drawn this line, this first line from here to this line here, and that would have been A. From this line to this line would have been point B. Okay, we don't have a load here. In your assignment, you got a load over there. Okay. Next step, in the inside of my members, we just number them 1, 2, 3, 4, and 5. Okay, so we use capital letters on the outside and numbers in the inside, the triangles. Okay, he's not sure how the Bose notation works. He wants to... Okay, so as long as you know on the outside we're working from force to force, this force to this force, this force to this force on the outside, and then inside we're starting on the left hand side, we number them 1, 2, 3, 4 and 5. Okay, that's the second step. The third step is to the first step is to draw my load line. That's free, it's a load line. Okay, now when you draw a load line, it's similar to the calculation we've just done to check if my forces are in equilibrium. All we're going to do this now is we're going to demonstrate that on a we can demonstrate this on a line, on a vector line. So again, guys, let's start from A to B. So from A to B, what force do I got between A and B? 20 kilonewton going down. Between B and C, how much do I got going up there? Here, 32.5, the resultant here. Between C and D, I've got 5 going down again. So all you do is draw a line going down, up, and down as the forces depending on the forces, the direction of the forces. Okay, so the first thing we need to determine is what scale do I work in. Now, we need to determine, you can count the blocks, like this example you'll see here, the blocks was counted. Now say, one block here, or 10 millimeters equals 2.5 kilonewtons. So let's keep to that scale. Let's make it a bit easier. I'm going to say 10 millimeters equals 5 kilonewtons. Okay, you pick your own scale. You can do any scale. On this scale they use 10 millimeters equals to 2.5 kilonewtons. Okay, that means for every 10 millimeters I draw on my graph here, it will represent 5 kilonewtons. As simple as that. So let's do the first one. Between A and B, from A to B, I'm getting a 20 kilonewton line going down. So how many millimeters will that be on my paper? 40 millimeters. Okay. So, and when you draw your load line, you see we worked on capitals over here. On your load line we will work on lowercase symbols. Okay, so from point A to point B is 40 millimeters. Okay, so you draw a physical line going down here 40 millimeters. Okay, from point B to point C, I've got the force going upwards of 32.5. How many millimeters will that be on your sketch? That's easy to calculate, guys. If 10 millimeters equals 5 kilonewtons, how many millimeters equals 1 millimeter? Okay, so for every 0.5 kilonewtons equals 1 millimeter. So quickly calculate, what is 32.5 kilonewtons going upwards? How many millimeters will that be?
65.
Thank you. 65. Okay, so this is 40. And this is going upwards again, guys. So from A to B was going downwards. From A to B. So we're going up now with 65. So this is 40. 65 would be here somewhere. So from B to point C. It's going upwards again. Okay. From C to D, will I go up or down now? Down. 5 kilonewtons. How many millimeters would that be? 10 millimeters. Okay, that is 40. 10 millimeters would be here. So my D would be here. Okay. From point D back to point A, how many millimeters will I get here? I've got 7.5 kilonewtons going downwards. How many millimeters would that be? 15 millimeters. Yeah. Okay, and it goes downwards. Okay, and we're from point D back to A. So D back to A, 15 millimeters. Guess where you end? right back at A. So all it means is I've gone from A to B, I've gone down. From B to C, I've gone up again. From C to D, I've gone down again. And from D back to A, I've gone down again. And it must always end back at A. But you see the problem here, guys. Look at my load line. It's so small. On your paper, I mean, it's going to be miniature on your paper. Okay, so if it's too small on your graph paper, enlarge it. When it's too large, guys, it's not going to fit on your paper again. So you determine your own scale. So it's important for you guys to at least practice this at home, because you're going to get this in the exam. And when you start struggling with scales in the exam, you're done for it, because time is a big issue. Okay, you've got 6 questions in the exam, 5 to 6 questions. And normally people don't finish in time. So normally I ask the guys start with this question, because it takes the longest. It's going to take you roughly 3/4 an hour to an hour to complete. And you only got 3 hours. Okay, so if you've completed one, it's about 30%. Then you need to go for the other questions, and that's going to take you also a bit longer than 2 hours. So time is your enemy. So practice this at home, guys. Otherwise you won't be able to finish this in time in the exam. Okay. My problem here is it's too small. I'm going to enlarge it now. So I've decided, no, this is not going to work for me. I'm going to use a different scale here. Okay, so in reality, I'm going to make it a bit bigger. If I want to make my load line bigger, what am I going to do here? Okay, so how am I going to do this? Instead of 10 millimeter equals 2 kilonewtons, I'll reduce this. I'm going to make this, let's say, 2 kilonewtons equals 10 millimeters. Okay. So let's see what happens here now. From A to B, 20 kilonewtons going down. How many millimeters would that be on your page? Yeah, that's right. So it's 100 millimeters. Okay, this is exaggerated now. It's not going to fit on your paper again. Okay, it's just to give you the idea. So from A to B, it's 100 millimeters. So I'm just going to present it here. Let's see which side we're working on. Okay, from A to B, it's 100 millimeters. Okay, then from point B to C, it's going to be 32 kilonewtons going upwards. So how many millimeters will that be?
162.5.
162.5. Okay. So this is 100. So here again. Okay, so it's going to be here somewhere. Okay, I'm just estimating this. In the exam you need to do a precise measurement. Okay, and then from C back to D, I'm getting a 5 kilonewton load going down. So 5 kilonewtons will be how many millimeters?
25.
25 millimeters. Okay, so you measure this back. So from C to D, 25 millimeters, so it's roughly about at this point here. And from D back to A, I've got 7.5 kilonewtons going downwards. So how many millimeters would that be?
37.5.
Okay. And when you measure this, it should end back at A. Okay. So we've gone up and down. So from A to B, gone down. Then we got from B to C, we got up again. So this line's been drawn up. From C to D was down again. And from D to A, and it balanced. Okay, that's your load line done. Okay, you can put some dimensions in here if you want to. But the first time you do this, guys, you'll see, just draw it in pencil on your page, because you don't know if your diagram is going to be left or the diagram is going to be right of your load line. We need to draw this diagram over here. It's called a Maxwell diagram or the Cremona diagram. Okay, so if your load line is done, that just recipe number 3. Number 4 is draw your, let's call it the Maxwell diagram. Okay, so when we draw the Maxwell diagram, we start on the different members. We start on A1. This is called member A1 now. What will this member here be called? A2. What will this member be called here? 2, 3. 2, 3. 2, 3. It's the two numbers splitting the two lines. Okay, the two members. So this member will be called what? D1. In this case, this member will be called B5. And this member here will be called A5. Okay, so each member has got a name now. Okay, so if I draw these members on my diagram, I need to first look what is on my diagram here, and then draw my diagram on here. So what I do, guys, let's start on member A1. This is called member A1. It's on a 45-degree angle. So what you do is you transfer this angle as it is to your diagram. Okay, I'm going to use, and please work in pencil, because if you make a mistake, you can't correct it in the exam. Okay, use a pencil, please. Okay, so from A to 1, it's a 45-degree angle, and I'm going to transfer it here. So all you do with a light line, just draw a 45-degree angle out from A in this direction. I only got an A here. Do I see a 1 on this line here? No. So all you do, guys, at the ends, that's my trick, I normally write a 1 here and a 1 over here. That means 1 is somewhere on that line, but I'm not sure exactly where on the line it is. How will I determine that? What I do is I look for a common member, D1 over here. D1, if I transfer this angle to my diagram, do I got a 1 somewhere on my diagram? No. But I got a D. I've got D over here. It's already on here. So what I do is I transfer this angle here. Again, you draw with your pencil. Draw a 90-degree angle here. And on it, again, you can write 1, 1, because that's the common member. It's called member D1. Where do they cross? Over there. Where they crossed, you can confirm that point. That is point number 1. Okay, so I'm going to make a dark pencil here, and I'm going to write 1 here. Okay, if that point is confirmed, you can draw that this lines from A to 1. A1 is in this direction, right? You can complete that in a dark pencil. So you know this line is confirmed. It's definitely over here. D1 is also confirmed. From D to 1 is also there. And you just draw that in a dark pencil. Let's go for the next one. We've covered A1, we've covered D1. Let's go to member 1, 2. Do I got a number 1 over there somewhere?
Yeah.
Yes, it's already here. Do I got a 2? No. Okay, so let's transfer this angle here. This angle is 45 degrees from point 1. So from point 1, 45 degrees angle. You draw us in both directions. And again, you can just make a little 2 at the edges to make sure you don't get confused. So that is line 1, 2. It means it's representing this member here. Let's see which is a common member. Member A2. This member here. Member A2 is in a 90-degree angle here. So I transfer this to, I've got to A. I don't have a 2 here. So from point A, which is here, I can draw a 90-degree angle out here. And this is called point A2, right? So I got a 2 and a 2. This 2 line is going in this direction, and this 2 is over here. Where do they cross? Right at this point here. So that will be called point number 2. And you just write a small number 2 next to it. There it is confirmed. Okay, because I've got a confirmed 1 and a 2 over here, 1, 2, you can draw this in dark pencil so you know it's confirmed. And also, remember A2. A and 2 is also on my diagram now, so you can confirm that. Is everyone with me right now? Okay, this is not that difficult, is it? Okay. Okay, next one. So we've covered 1, 2, we've covered A2. Let's go for member 2, 3. 2, 3 is in a 45-degree angle. You take your, you can, if you want to use your set squares, 45-degree set square, you can use that. Just transfer this angle. But on a graph paper, guys, you've got blocks. So if you want to draw a 45-degree angle, you just draw it from the corners to the corners. You see that, guys? So you don't need to use a set square. Okay, so let's go back to member 2, 3. So 2, 3, 45-degree angle. 45 is over here, and I draw it out here. Okay, that's called member 2, 3. So you make the little number 3s here at the side, each line. Let's see which is the common member. Member C3, and that is in a 90-degree angle over here. From point C, where's my point C is over here, 90-degree angle. Draw this in both directions, and I'm going to call this number 3 and 3. So this line is C3, and my other 3 line is over here, crosses here from B3. Again, where do I cross? Right over here. Where the 2 lines cross, you call this number 3, and that's a confirmed point again. Okay, so member 2, 3 you can complete. And also member C3. You can draw this on your diagram. Okay, there it goes. Okay, which is the next member? Member 3, 4. Again, this is in a 45-degree angle. We don't have a 4 on there, but I've definitely got the 3. So 45 degrees from this point here. And that will be member 3, 4. So 4 and a 4 here. Which is the common member here is member A3. We've got the A here. There's the A. So from point A, 90-degree angle. And this way, this is also called point 4 and point 4. And this point 4 and this point line 4 is going to cross over here. And that will be called member 3, 4. You can call this number 4. Okay, everyone okay with this? So it can get very complicated. You'll see the one in your notes. It's going to take you to do that example. It's going to take you an hour at least to draw it out. It's complicated. The one you're going to expect in the exam is similar to this. So just follow the rules, guys. Just draw your lines. It will make sense at the end. Okay, we've done 3, 4. Let's go to and A4. A4 is done. Sorry, A4 is here, so you complete that. Let's go to the next one. Remember, let's go to 4, 5. So 4, 5, 90-degree angle from point 4, and you just draw it in there. 4, 5. Okay, and the common member here is 5, B5. So from B, you transfer this angle over here, and this is called member B5, so you can call this a 5 over here. Where do they cross? 4, 5 is going in this direction, so 5 is over here, and I've got the 5 over here, so they cross roughly down here. I'm going to cross over here. Okay, that's going to be called point number 5. Okay, so B5 and 4, 5 you can complete. I'm just going to draw this in here. Obviously, I'm not using graph paper, so my diagram is not going to work out exactly. Okay, so we've covered 4, 5, B5. So the last member we need to complete is, remember, A5. This member here, A5. So I've got the A here. It's going 45 degrees out from A. So this 45-degree angle I copy over here. Okay, it's not really 45 degrees. I'm not using a graph paper or a set square. So if you use a 45-degree angle, it should cross here with 5, and you know that it is complete, and you can draw that in. Okay, so if you made a mistake on your load line, you can see your angles won't work out exactly. So it's important, guys, that you, when you work on this load line, work to a 1 millimeter accuracy. Okay, so make sure that you don't make a mistake on there, otherwise your whole diagram won't work out. Okay, so this is called your Maxwell diagram or the Cremona diagram. If you got this on your graph paper, it will look like this. You'll see it looks similar to ours, not exactly the same as the one on here, because the numbering they used on this diagram was a bit different. Okay, but when I mark it in the exam, guys, I'm not going to look for your numbering. So let's keep to a convention. We always start the Bose notation left of your reaction A. So my A will always be on the left-hand side of my reaction A. Okay. After we've done that, all we need to do now is measure. Okay, so step number 5, measure.